Start recording. Okay, sorry about that. Yeah, so A complement is the universe without A. So if this box is our universe and this circle is A, then that shaded part is a complement. Yeah, yep, because the empty set is the set that doesn't have anything in it, and the universal set is the set that has everything in it. So yeah, so empty set complement is the universal set, which read the other way says the universal set is actually, sorry, and then the universal set complement is equal to the empty set. So the empty set is a subset of the universal set, right? The empty set is a subset of every set. That's a good point. I'm pretty sure this is true. Y'all should look it up though. um, yeah, let me just put a box around that and say look that up. But I'm pretty sure that's true. Okay. It's also a terrible arrow. Cool. So does that answer your question on P complement? Yep. So what other questions do you guys have? Yeah, floor is open. Uh, I can't really see that in my screen because I've got screen sharing on. Let me just stop screen sharing for a sec so that I can actually see your camera. Oops. Stop share. There we go. Hold it back up. And yeah, that's kind of blurry. Yeah. So yeah, you would just leave that empty. Because if you put squiggles in there, that would be the set containing the empty set. Okay. I was gonna say so I mentioned last time it's like I don't prepare lectures for this. I just am here to answer your questions. So if nobody has questions, this is going to be a very quiet session. Okay. So that was one of the proof problems. Let me see if I can find the exam. Let me just go to Canvas. Uh, mhm. Mhm. Yeah, you could do that. If the proof is like there exists some and you don't think it's true or you think it's true, then you can just um, you pick one. Well, so if let me just pull up the question. Let's see here. That's 3A, 3B. So yeah. So whenever you've got some proof that says there exists some X and Y in the universe, if you think that this is true, then you just have to provide a witness to show that yeah, for something that works. But in this second one where it says for every, if you think that's true, then you have to provide a proof. But if you think it's false, you just have to find one instance where it's false. Does that make sense? Cool. I did a proof witness for some for every table, I think, in the last session. And Quinn made a video on it that I think he posted. But yeah, if you've got an argument, or if you've got something that's like, for every XY in the universe, this thing is true, and you think that that is a true statement, you just have to find one where it is true, because then you've shown that there exists one. But if you think it's false, then you have to show that no such pair of things exist. Well, it's not that it's not going to work for every single case, but that there's no case for which it works. And for every case, if you want to prove it true, then you have to provide a proof of why it's true for every case. But if it's false, you just have to find one instance where it's false. Yep, you're welcome. Mm-hmm. Mm-hmm. Want to see part 3? Uh, so it's asking that for every x there exists. It's saying that for every x in the natural numbers there exists some y in the integers where x times y is less than 0. And so if you think that so this would be, I guess, a for every proof, because we're saying for every x. Um, so if you wanted to prove that for every, you would have to provide a proof. Yeah. So in his notation, multiplication is just the juxtaposition of numbers. So if you've got like 0 times x, that's how you would write multiplication. Just with the parentheses. Don't use the star, don't use the times. It's just juxtaposition, either both with parentheses, or if they're just letters, you can write it as AC, or you could write it like AC or whatever, or AC, but don't use these symbols. Okay. Any other questions? This is pretty quiet. I thought there would be more questions. Yeah. Um, yeah, what's up? Mm-hmm. Which packet is this? Which packet is this? Set notes? Okay, let's check that out. Which page? Page 26. Wow, he's really expanded the set notes. Page 26. Okay. And so is it one of these symbol, like this symbol? So I'm at the bottom of page 26. Well, oh, this one. Yeah, sorry, yeah, it's page 26 in the PDF, but does he start counting his pages at 0? Of course he does. Doesn't make sense. That's not a title page. That has information on it. Anyway, he always starts counting at 0. It's the first natural number. Anyway, yeah. So this notation is introduced in the functions packet, where you've got, let me just pull this off. Whoops, why did that come off? Move that over there, and yeah. Can I have that and still write over here? Let me just copy this onto a page. Is equal to, is defined to be equal to thing that takes s. This is read as, I'll just write it all out and then I'll read it. Okay, so this is how functions are defined, where we've got the name of the function, from last lecture, this colon is read as is defined, and the equal sign is to be equal to. And then this is the thing, like, so this, I'll just read it out. So this is new is defined to be equal to the function that maps s to nu of s for sets going from the universe to the natural numbers. So this is your input, your function input, and this is mapped to. And then this is the output. And this is your source set, or in your pre-calc courses or your calculus courses, you would think of this as the domain. And then this is the not range, this is the target set, which would be the codomain. So this particular function, nu, this is the Greek letter nu, which is the Greek letter for n, and it takes a set and maps it to the number of elements in that set. So it goes from, the source set is our whole universe, because S is some element in the universe, and it maps it to the number of things in that set, which is a natural number. But yeah, the arrow here is the function mapping, or the relation mapping. Mm-hmm. Well, so the universal set is defined as the set of things that we're talking about in this art, like in whatever it is we're talking about. And if you don't have another universal set, because that's outside of the scope of the things we're talking about. So if you're trying to think of it that way, then the original universal set wasn't really the universal set, or you're redefining the set of things you're talking about. So the question doesn't quite make sense. Does that make sense? So are you asking about relative complement? So like A without B, where yeah, if you take the universe, or I guess a set without itself would just be the empty set, but it's not the universal set with another universal set, it's just with a copy of itself. Does that make sense? Cool. And, man, I cannot find a good place to put this picture thing. Can I just hide this? I don't really want to see myself. Yeah, that makes it smaller. Oh, my cat is yowling. Any other questions? Sure. Which one? Yes, the 24. So, like this one? Not including this one? Okay, so this one. Yeah, sure. So this is, whoops, I need this to be the pencil. So this was, I already forgot. It was B comma C intersect A comma C, and then all of that crossed, or the Cartesian product with itself. B comma C intersect A comma C. Copy that right? I believe so. Okay, yeah. So we can start by oh yeah, so this is the set containing that one element. Okay, sorry. I missed the brackets, so it's this outer brackets that I missed. Good catch. Cool. So if we do, so first we can just take care of, and I'm just going to scroll down for a bit. First we can take care of B comma C intersect A comma C. So that's equal to, so what's the intersection of these two sets? Yeah, it's just the set containing C. So if we go back up to our original expression and put that in, this is the set containing C crossed with the set whose only element is the set containing C. Right, you can think of, so these parentheses, we've only got one element, so I dropped the parentheses. We could write it like this, and then because that's the only element in there, cool. So then what's the algorithm for the Cartesian product of two sets? Right, we draw the word tree, right? And then how many blanks are in this tree? Have you guys, I don't know if this, I haven't read through the notes package. I just remember stuff from his lectures. Have you guys, yes, two blanks. And then, so how many things can go in this first blank? Yeah, just one. And what's that one thing? Yeah, C. And then what can go in this second blank? Right, so we just have one branch, and this is C set containing C. So this is equal to the set C comma set containing C. Does that make sense? Yep, you're welcome. Good catch on the extra parentheses and braces. I totally would have missed that. It would have been a completely different problem. So what else do you guys want to see? I can find them. 25. So like these proofs. Yeah, this one. So do you know what the double equivalence bar means? Like how to read it? Yeah. So that's like if and only if. It's the you might be familiar with this notation, where it's the, excuse me, double-headed arrow. That's what it is. The double bar like that is, I guess, equivalent to this symbol that you're familiar with. Yeah. And the single arrow is equivalent to the single conclusion bar. So in this one, both sides imply each other, and in this one, only the left side implies the right side. And left side becomes top and right side becomes bottom. Actually, so would it be helpful if I just like read this in plain English? Okay, so this is there's so we've picked some A in the universe and some B in the universe and then some X in the universe, and we've noted that X is a member of A without B. Actually, before I do that, it's asking us to prove that for every A and B in the universe, A without B is equal to the intersection of, sorry, yeah, is equal to A intersect B complement. So that's what we're trying to prove. So at the start of our proof, we pick some generic A in our universe and some generic B in our universe, and then some generic X in our universe. And we note that X is a member of A without B. And so if X is a member of A without B, that's by definition, that means that X is in A, but X is not in B, just by the definition of complement. So this means from this it follows that X is a member of A and X is also a member of B complement, because if X is not a member of B, by definition of complement, it means that X is a member of B complement. And the white space in between is an implied and, so here he's making it explicit, where this is X is a member of A and X is a member of B complement. Therefore, so by definition of the intersection, if X is a member of A and X is a member of B complement, then X is a member of A intersect B complement. So we've shown that for a generic X, a generic A, and a generic B, that this is true. So from that, we can conclude that for every X in the universe, X being a member of A without B implies that X is a member of A intersect B complement. So from this, it would follow that A complement is equal to A intersect B complement. And so then from this, it follows that for every A and B in the universe, A without B is equal to A intersect B complement. Mm-hmm. Oh yeah, it's totally intimidating, especially because this is the first time you're having to do that. Um, I guess the way to practice it would be to like go into the Sham's outline for discrete mathematics. If you go into that book and try to translate some of their proofs into like this notation, that's a good exercise. I guess the only problem is then how do you check that? How do you know that your notation is right? And I guess to that I would say post it to the Discord and maybe tag the tutors, and if one of us can get a chance to look at it, we can take a look. Um, though, just keep in mind that like Quinn's got a full-time job, and both Chris and I are full-time students, so we may or may not be able to get back to you. But it would also be helpful to share it with your other classmates, to see if any of them have any insights. Yeah, it's definitely the hardest part of the course. But the more you do it, so the more you do it, and if you do it correctly, the better you'll get. So you guys know the phrase "practice makes perfect." Well, it's wrong. You need to forget it. Practice doesn't make perfect. Practice makes permanent. Only perfect practice will make perfect. So the way you practice something will be the way you perform it. So if you practice something wrong, you do it wrong every time. Um, so only perfect practice makes perfect. Something that I would note about this is I'm a little confused about why he says that A is an element of the universe and B is an element of the universe and X is an element of the universe. Because I think these membership symbols should be subset symbols. A is some subset of the universe and B is some subset of the universe, and then X is a member of the universe because the universe is like the set of things we're talking about. Um, and if A, B, and X are all members of the universe, then to me that seems to indicate that they're all of type element. And then you can't do this complement operation with things of type element. That only works with things of type set. Does that make sense? Probably. I guess it again it depends on the situation. But yeah, if you're trying to say that A is some set in the universe, I think that that should have the subset notation, not the element notation. Um, the difference is like if this is our universe, this point here in our universe, that would be X. And like this collection of points, that would be A. And this other collection of points, that would be B. Where X is a single point in our universe and A and B are subsets of our universe. A would be a subset of the universe, and same with B, be a subset of the universe. It's really hard to write with the stylus and stuff. Any other questions about the exam or the notes packages or anything else? Mm-hmm. Let's see here. So for 1A, so I think the work is in the box. Like this box, I believe this box counts as work. He did not have these boxes when I took the class. He's had them for a couple semesters now, though. So you just write your JK in here, you circle yes, no, and then by inspection of the yes, nos, you can fill out your A. But I would double check with him on that. But that is my understanding of how this works. Sure. Is that on the exam or is that just in the notes package? Oh, right. Okay. So there's this, like, so for example, question 2B, right? Okay. So he started using a different notation, base case 0. It used to just be BC. But yeah, so the base case, so recursive arguments are one where you have some case that's true at the beginning, some base case that is just like this is where we're starting, and then you have some recursive step that says for every n in the natural numbers, something is true. So actually, let me run upstairs and grab my exam because I don't want to do this particular question because this is, yeah, I will be right back. Yep. You guys can keep talking though. My headphones are wireless and they come with me. Yeah, I can demonstrate that whenever I get back. Okay, so let me stop sharing my screen for a sec. So yeah, so if this is an exam and you open it up, this is the page, this is the facing page. So like, this was my first question. Over here is the answer page, and my work was over here on the facing page. Okay, so go back to sharing my screen. And we're looking at, okay, so in my, when I took this, it was actually question 2C. So yeah, so let's see here. So so for me, I had lowercase x was equal to nu of capital X, lowercase y was equal to, and this was in the natural numbers, lowercase y was equal to the number of things in y, which is in the natural numbers, and z was equal to the number of things in capital Z, which was a member of the natural numbers. And my base cases were, so BC, what's his notation like now? Okay, so I had BC 0 was that S0 was equal to X. BC 1 was that S1 was equal to Y. And BC2 was that S2 was equal to Z. And then we had the recursive step where for every n in the natural numbers, S sub n plus 3 was equal to S sub n cross S sub n plus 1 coproduct S sub n plus 2. So, and then the first question that I had was to compute S3. Okay, so to compute S3, we look at our recursive definition and see if we can rewrite S3 so that we're using this notation here in the subscript. So I can write 3 as 0 plus 3, right? So this is S of 0 plus 3. And so that part becomes n. So then if n is 0, that means the subscript of the first one is 0. And then the subscript of the second one is 0 plus 1. And then this is 0 plus 1, and this is 0 plus 2, which is equal to S0 cross S1 union, or sorry, coproduct S2. And so going back to our base cases, well, S0, and I forgot colons, S0 was defined to be equal to capital X, S1 was defined to be equal to capital Y, and S2 was defined to be equal to capital Z. So that means this is equal to, what was it again? Just X, Y, and Z, right? Yeah. Capital X cross capital Y coproduct capital Z. And that would be the end. This would be what I would write on the work page, and then on the answer page it was like S3 equal to X cross Y coproduct Z. And that was worth 1 point. So does that start to answer your question? Yeah, well, so that's computing S3. So then 2 questions later, let me create a little bit more space. Right. Really need to get OneNote working, or does anybody have a recommendation for a OneNote substitute for Linux? No? Okay. I didn't think so, but I figured I would ask. Okay, so a couple questions later, it asked me to, whoops, compute S4. So remember that our S is in terms of n plus 3. So for S4, what would n be? And yeah, and we would write 4 is 1 plus 3. So this would be S sub 1 plus, and then what was our recursive? It was n plus 1, n plus 2. So this would be S sub 1 cross S sub 1 plus 1 coproduct S sub 1 plus 2, which is equal to S1 cross S2 coproduct S3. And I need more space. And so this, well, S1 was Y, and S2 was Z, and S3 we found in the previous question. It was X cross Y coproduct Z. This is then X cross Y coproduct Z. And that would be the answer. And I would write just this part, just that part would go on the answer page. And another part of this question, which is, I think it's going to be part of yours as well. Whoops. Yeah, so here you have to then find the number, like find the number of things in the set. So I'll go ahead and do that with my example as well. So give me more space. Okay, so my S3 was equal to X cross Y coproduct Z. And we want to find nu of S3. Well, that'll be equal to nu of x cross y coproduct z. Okay, so how do I do this part of the problem? That's a non-rhetorical question. Anybody have any thoughts? Well, so we go over here into our notes package, and actually it was really close to what we were just looking at. It's on page 27 of the notes packet. We've got a bunch of rules about cardinalities. So one of these rules is for, well, what if you've got the cardinality of S cross T, where S and T are sets, and what if you've got the cardinality of S coproduct T, or S disjoint union T? Have I been using the word coproduct wrong this whole time? Somebody? No. Okay, so we use these rules to move forward in this question. So in my question, this part is playing the role of S, and this part's playing the role of T. But if you write it like this on the test, that's not going to fly. So let's use the proper notation. So the rule that we're trying to use, and there's a couple ways to write it. This is my preferred way to write these kinds of things. The rule we're trying to use is the cardinality of ST is equal to cardinality of S plus the cardinality of T. So from the fact that this is true, it follows, pretend that's a straight line, it would be drawn with a ruler if I was on paper, that if S is replaced with X cross Y and T is replaced with Z, don't forget to close substitution brackets, then the cardinality of X cross Y T is equal to the cardinality of X cross Y plus cardinality of Z. And so let me actually just come here and erase this stuff. And then we put that up in our work. So we can, if we reference this as like, in my exam, this is question 2C part 3. 2C dot 3, and I will call this part 0 because this is kind of where I'm starting. I could label this piece down here as 2C part 3 part 1. So then from this line to this line, it looks like I have skipped a step, but if you go to my next index, you will see the work there. And so we found that that was cardinality of X cross Y plus cardinality of Z. So now we have to handle this X cross Y business. And hey, we have a rule for that one too. So let me give myself a little bit more space. And so this would be 2A, question 2A, part 3, part 2. And we have that the cardinality of S cross T is equal to the cardinality of S. And in his packet, he did that thing that I told you guys not to do. He used the X for multiplication. You can either, I would avoid using that on the test because he might forget, but then you could point him at the packet and be like, hey, Dr. Bagchi, that's what you wrote. But then you actually have to like follow up, and that I find that to be annoying. So you can write this as just multiplication with juxtaposition. So from the fact that the cardinality of S cross T is equal to the cardinality of S times the cardinality of T, it follows where S is replaced with X and T is replaced with Y, that the cardinality of X cross Y is equal to the cardinality of X times the cardinality of Y. And then we go back up here, and now we've got the cardinality of X times the cardinality of Y plus the cardinality of Z. And given at the beginning of the problem, we've got that lowercase x is defined to be equal to the cardinality of x, lowercase y is defined to be equal to the cardinality of y, and lowercase z was defined to be equal to the cardinality of z. So we can go back down to our problem here, and that means we've got x, y plus z. Whoops. Z. And then this piece would just go on the answer page. And so this stuff would go on the work page. And actually, let's see here. This would have been question 2C part 3 part 0. And that would have gone on the work page and been put in a box. And pretend this is a box. It is not. And then this part we could have labeled as 2C part 2 part 0. Oops, that should be a 0. And it would, again, that would go in a box on the work page, or yeah, on your work page, and then the answer would go on your answer page. And again, pretend that these are drawn with a ruler parallel to the pages. And each of these would have been in their own box that extends, like that completely cuts them off from other sections and doesn't look like a conclusion bar. And so that's how you would show your work on the facing page, is by essentially putting all these things in boxes. Whoops, why are you doing that? And then just this would go on the answer page. Man, this is really hard to write with. Okay. Any questions on any of what I just said? On formatting, like what goes on the work page, what goes on the answer page, or how to show substitution. I could show you guys this in a different way, which actually I think I'm going to do that. There's another way that Bakshi shows substitution. I personally like substituting rules into rules, but something you will often see in his notes. I'll just do cardinality of S cross T. He'll do the substitution actually here. Let me see if I can find it in his notes, because I stopped writing it like that a long time ago and don't always remember how he does that. This is the notes, right? Yeah. Does he not do it in this set of notes? Does anybody know off the top of their head a page where he shows substitution in the notes? Huh, okay, well, I know I've got it in the Math 270 packet, so let me just find that for a sec. Where was it? Yeah, there it is. That's the exam. That's also an exam. Oh no, that's that's an exam discussion. I think it was problem. Problem notes 1. Or am I already looking at that? It's not looking at that. There we go. Like this, where he'll use the substitution brackets off to the side. Oh yeah, here we go. Yeah, this is what I was looking for. He like never used the upside down 3 dots in when I took this class. But yeah, this is what I was talking about. I like never used this notation, so let's see if I can parse this out. So this is back here. So we had our original expression x cross y. And so let's take x and replace it with s, and y and replace it with t. So that's equal to nu of s cross t, and that is a rule from our packet that this is, we had a vertical bar over here, and we had that nu of s cross t was equal to nu of s nu of t. So this is nu of s nu of t, and we were allowed to do ditto marks for the substitution brackets, so we didn't have to write this every time. And so this would be equal to x nu of x nu of y. I personally don't really like this notation. I find it to be kind of confusing. So I generally try to substitute directly into rules, which you have to do off to the side. The dead silence is kind of like the blank stares I get in if we were in a classroom. Yeah, the script P thing, that looking thing, that's the power set, yeah. Well, so the power set spits out a set. So 0 and 1 are numbers. They're not a thing. They're not an object of type set. So the power set wouldn't just spit out a 0 or a 1. So if we had the power set of the empty set So what is what is the power set? What does that operation do? Yeah, it gives you all possible combinations of the elements. It's a set containing all of the subsets of whatever set you're talking about. So what are the elements in the empty set? Well, the empty set it doesn't have any elements. So what's the only subset then of the empty set? Yeah, so the power set of the empty set would be a set containing the empty set. And this outer set isn't an empty set. This is a set whose only element is the empty set. Does that make sense? I think he had some power set, like some notes on power sets in here somewhere. Yeah, so if we then took the power set of this, so this would be the power set of the set containing the empty set. So then what are the subsets of this set? Yeah, so the empty set, yeah, the empty set is definitely in here. And then what's the other element? Yeah, you would just have the empty set again, right? Right, because the empty set's a subset, and then the other element is the empty set, right? But that is, you've got the empty set in there twice, so that's just the set containing the empty set. So that's kind of weird, right? Because yeah, we went through and we listed all of the possible subsets of this, and it just turned out that the only element in there was the empty set. But if you have a set whose elements are the empty set and the empty set, since we're not talking about a multi-set, this is just a set containing the empty set. It's kind of weird. Yeah, I mean, we just followed the rules. One of the things to keep in mind is that math is a game, and you can't play game if you don't know the rules. Bakchi's got his rules written in a very specific way, and you have to play the game in a very specific way. Like when I'm yeah, I would say when I'm tutoring people in like Calc 1 or Calc 2, it's not usually that it's usually that they understand what's going on in the calculus class, but they don't remember the rules of arithmetic or algebra. So I guess in this class, if you're on an exam and you can't if you can't figure something out, just try to find what rule you need. Like in the previous problem that we were considering, whoops, that's too far back. To get from here to here, we had to know a rule, and then we had to know how to use that rule. So you can't play a game if you don't know the rules. If we didn't know that rule, we would just be completely stuck. And if we wrote anything besides what is already there, it would be nonsense because we wouldn't be playing by the rule. Unless there's some other rule that you can find. Yeah, so there's a good question on this exam about the difference between did I close the exam? I must have closed it. The difference between element hood and subset. That's often a point of confusion. So that's the sets notes. That's the sets notes. I just minimized that. Okay, I guess I closed the exam. So question 2A tests that. So if you see the symbol for element, that means it's asking, does one appear between a brace and a comma and a comma, or a comma and a brace? Actually, let me see if I've got a similar question on my original exam. He was a little more cryptic with mine. Yeah, so we'll just go with this. I'll just make up an example. So like, let's say we've got the set y and the set containing x, and that's one of our sets. Let's just call that v, and let's call x the set x, y the set containing x, and the set containing y. And let's say I ask you the question, is Is X an element of capital X? Is this true or false? Anybody? True, yeah, right, this is true. Because if we look at our set X, there's X, it's between a brace and a comma. It's an element. If I asked if X was a subset of X, is that true or false? Right, but this isn't a curly braced X. This is just an element X. So this would be false because this is something of type number or element. And actually, let me just note up here that X and Y are natural numbers, just so that we're clear on what X and Y are, that they're not other sets. They are natural numbers. So we can't have a natural number be a subset of a set. That actually just doesn't make sense. But if I had the set containing X, is that a subset of X? Would that be true or false? That is true. Why is that true? Well, so what does it mean for a set to be a subset of another set? So if A is a subset of B, what's true? Yeah, but you can't really use diagrams on proofs. So the definition in the packet is that A is a subset of B if for every X in the universe, X being a member of A implies that X is also a member of B. So if we consider this over here, our set A, what are the members, what are the elements of our set A? Well, it just has one element, and that element is the number X. And that number also appears as an element in capital X. And so now let's take this a level deeper. So what if I asked you, is the set containing X a subset of X? Oh, and this was true. Is that true or false? Okay, so why do you say it's false? So this set X, we can also, if there's only one element in there, we can call that the singleton. So this is the singleton of X, or just the set containing X. This is an element in the outer set. So if I just, let me just say that, like, I don't want to use B because I used it up there. I'm just going to define some set P and say that it is the set containing X. Actually, no. I wanted to just be the set X. We could then rewrite this as the set containing P, where we understand that P is itself a set. Actually, hold on. If we actually, let me try to explain it in a different way. If we just look at this thing here, this is an element of our outer set. This set X is just an element in our outer set, the set containing X. Actually, let me ask a different question. It might be a little easier to see it this way. I'm kind of losing, kind of getting you guys lost, I think. That's a Y. X. So this is, so is V, which is equal to the set containing Y, comma, the set containing X. Is that a subset of X? True or false? Right. Why is that true? Right. Yeah, so this one is true because y appears as an element in both v and x also, the set containing x also appears as an element in v and capital X. So because this thing was in v and it was also in x, and this thing was in v and is also in x, and since that's all the things in v, we can say that v is a subset of x. Would we say that v is an element of x? Does this whole thing, that's asking, does this whole thing appear between a comma and a brace, a comma and a comma, or a comma, yeah, or a brace and a comma in our set X? Does this whole thing, the set containing Y and the set containing X, does that whole object appear in X? No. Right, so this would be false. Is that starting to become clearer? Cool. Yeah, let me pull it up. What page is it on? Yeah. Where do you have that? Yeah, so A intersect itself is itself. I'm not sure what you mean. So the set containing the empty set, like this. What do you mean by with? Like that's there's another set over here. So there's another set over here that is the set containing the empty set. Uh, no. So let me just clarify. Is this what you're saying is the other set? So we have. Okay, so we just have the set containing the empty set twice. What? So let's see here. This was A, and this is also A. So we would just have A intersect A. Yeah, which should just be equal to A. Yeah, because this we could redefine this and just say like lowercase x is defined to be equal to the empty set. And then we could write this as A is equal to x, the singleton of x. And then it's pretty easy to see that if you've got the intersection of these two things, that just contains x, and that's just A. If you've got x intersect x, that's just, whoops, equal to x. Yep. So what was the other question that was solved by introducing this x, if you don't mind me asking? Where? Say again? Yeah, so like little b, like an element, or calls it the counting. Oh, okay. Oh, the cardinality. Yeah, this V looking thing. This is the Greek letter nu, which is the Greek letter for N, which is the first letter in the word number, and the cardinality is the number of elements in the set. Yes. Yes. That is correct. Yeah, I just wouldn't think about it too hard. It's a set that doesn't have anything in it. It's like if you have a basket with nothing in it. It just has 0 things in it. It's just an empty basket. But then if you take that empty basket and put it inside another empty basket, then your outer empty basket has the inner empty basket. It's just like that. And now your outer empty basket has one item in it, which is that inner empty basket. Yep. Let me go back to set notes. Mm-hmm. So let's see. Let me just back up. Okay, so I'll just do this example over here. So we've got A1 cross B cross 1, 2, 3. Yeah, so we write the word tree, and this has 3 blanks. So the number of blanks is equal to the number of sets that you're taking the Cartesian product of. And the number of branches at each blank is equal to the number of elements in that set. So this first blank will have 2 branches because there are 2 things in the first set. So we have A blank blank and 1 blank blank. Oh, wait, there's 2 B's somewhere? Oh, oh yeah. So here, this first line is different. So that first line is wrong. That's a typo. Because if we do this out on the first line, we should have the things in the set in this first set. We don't have an A and a B in the first set. We have an A and a 1. So that should be A1. So that's a typo. Yeah, so there's going to be typos in here. If you find a typo, send him a message and be like, hey, you have a typo. Whenever I was in his class, I would mark up the packets with a red pen and then give them back to him and be like, here's all your typos. And then he would print us new packets and I'd have scrap paper. Now you're just going to end up with a bunch of files instead of a stack of paper. But yeah, that's a typo. That should be a 1. Because if we actually finished this problem out, we would then have the only thing on the next line is a B. So both of these just have like 1B blank, and then the last one is 1, 2, and 3. So this would have AB1, AB2, AB3, 1B1, 1B2, 1B3. Yeah. Yeah, because he copied his mistaken work up here. So that would get, if you did it like that, you would get no points. The form is correct, but the answer is wrong because that's not what's in the first set. So and I'm just going to, let's just define this as A. So one thing that you can always do is take a letter and define it to be equal to some long string of characters. Me personally, I'm lazy. I don't really like writing a whole lot, so this is something I often do where I just say A is defined to be equal to this string of characters, so that then I can write just that A is equal to, and then we already know that it's that long string of characters, and I can just write the answer here. So this would be AB1, comma, AB2, comma, AB3. Whoops, need some commas in here. Comma, 1B1, comma, 1B2, comma, 1B3. And then braces around all of that. So yeah, that would be the answer. And actually, I got an extra dot, and oh, I erased the whole 3. Yeah, so that would be the answer to this example problem. Yeah, so that's a typo. To answer your original question, that's a typo. Yep. Like I said, if you find a typo, just send him a message and be like, "Hey, Dr. Bagchi, I think there's a typo here." I've seen a couple announcements like announcements or messages that he sent out that's like students have been sending him questions about typos, and some of them are typos, and then he explains some of them. If you've got questions like that, send them to him. He likes that kind of thing. And since you're not in class, so one of the things that was always really stressful about his class is if you ask a dumb question, he tears you apart in front of the class. And now if you ask a dumb question, he just sends you an email. Unless he decides to then make it an announcement on Canvas, but I don't think he'll do that. Oh yeah, yeah, it was one of the best parts. Um, oh, I'm gonna mention again, if you weren't here at the beginning, put your name in the name and J number in the chat. That's how we're taking attendance. Okay, yeah, I've had my chat minimized. Let's see here. Proof or a set within a set, or can we write by inspection? Let's see here. For the questions in 2A, we have to use proof or proof of a set within a set. Let me just go back to 2A. That's this question. So yeah, you can just write. I don't know if it's proof or witness. He added this after I was in his class, but you would circle yes, and then yeah, I would ask him or one of the other tutors because to me in this particular question, it's not really clear whether it would be a proof or a witness, but the reason why is by inspection. Okay, cool. Then go with that. If he's posted examples in exams, an example of this particular question and their proof, then circle proof. For question 2B? Uh-huh. Well, so let's see what Sn is. Well, no, so the cardinality of S0. Wait, so for formulated conjecture for the value of n and x, cardinality of xn equals 0. Yeah, I don't know why he's got that there. Formulate a conjecture for the value of in terms of x and n. Yeah, this seems to just be in the wrong spot. That should really be up in this area. Like, let me show you the. I'll just turn on my camera here. Let me stop sharing. And yeah, so that should be like up here, something like that. Maybe. I mean, I'd have to work this out to be able to really give you an answer on that. But yeah, I don't know why this is here. Or, oh, okay, wait, hold on. Can you go over what the coproduct is? Yeah. Let me finish talking about this for a sec. So, formulate a conjecture for the value of Sn in terms of, I don't know why he has that here. And actually, my interpretation was wrong because that would have just been S sub 0. That would have gone up at the top. So maybe he's asking you to prove or disprove this statement, or maybe this is a typo. That's a question for him. Okay, sounds good. So let's pull up coproduct. Coproduct. Yeah, he's using this symbol. So the coproduct so this is an operation that creates a set of disjoint. You can think of it as the disjoint union. And I'll just do it with an example. And something that can get kind of confusing is that sometimes this is an operation and sometimes it is a property that two sets have. So I'll demonstrate this operation. Over here. So this is A coproduct B as an operation. Let's say, let me get rid of this. Let's say that A is equal to the set containing A and B is equal to the set containing B and C. So if we did A coproduct B, that would be equal to, and using our definition of coproduct, that would be equal to A cross 0, the set containing 0, union B cross the set containing 1. And so that would be the set BC cross the set containing 0, union, whoops, not universe, union, the set containing, oops, and I wrote the wrong set for A. This was AB. Cross 1. So, whoops, that's not the right symbol. So this, I'm not going to draw the trees because that would just take a long time. I encourage you guys to do that on your own. So this would be the set containing A0, comma, B0, union, the set containing B, comma 1, comma, C, comma 1. And if we take this union, we get A, comma 0, B, comma 0, B, comma 1, C, comma 1. So as an operation, it takes two sets that might overlap, because see, both A and B have this common element, lowercase b, and it creates a union of the two sets where you can figure out which elements came from which parent set. So like all of the stuff that originally came from A is tagged with a 0, and all the stuff that originally came from B is tagged with a 1. And you can actually do this with however many sets you want, and you just keep incrementing the number, like 0, 1, 2, 3, etc., however many sets you want to do this with. Another instance you might see this is as something that can have a truth value. Like you might see like A, B, and this would have a truth value of false. It could have a truth value of, actually here, let me be a little so this, okay, so here's where notation gets weird. So this is now in the set true. This is an element of the set true or false. This is either true or it's false. Does that make no? That nope. I'm just not gonna do that. I'm confusing myself a little. This can either be true or yeah, can be false. So like if our A and B are defined as above, if we did A union B, oh, and actually let me back up to talk about what that is. Disjoint sets are sets that don't overlap. So if this is A and this is B and this is our universe, A and B here, this would be A and B, that would be true. Those would be disjoint sets. But if we had something like this, where they overlapped, this would be false. So as an operation, it takes two sets and makes a union of the set where each element in that union, you can map it back to its parent set, and you've got the number of things in the resulting set is equal to the sum of the the cardinality of the resulting set is equal to the sum of the cardinalities of the original sets. Or put differently, you've got the sum of A coproduct B is equal to the sum of A plus the sum of B. So maybe something that I've been confusing for a while is the operation disjoint coproduct versus the property a set can have as being like a disjoint union of sets. Okay, that was very rambly and confusing. I'm sorry. What part in there confused people? I will try to clear that up. And let me check the chat. I think be viewed as placeholders. Kind of. Yeah, they're it's more of like an indexing system as opposed to like a placeholder. Cool. Also, I can't tell if you're just shouting or you've just got caps lock on. Not shouting. Okay. So what's the difference between a proof and a witness? So a proof is you've got a bunch of statements that go to let me. So I think I saw somebody in the Discord had a pretty good explanation for this. It's kind of like think of it like a trial where like you're trying to prove something true or false, and the one, I guess the prosecutors are trying to build a case to show that whatever they're trying to prosecute is true, but um, if the defense produces a witness that contradicts that, then you can think of that kind of like the witness is if somebody's making a claim and you've got a witness that says that claim is false, you just show that witness and you're done. A proof is usually like a collection of I can't think of the words right now. Usually a series of steps. Yeah, do you maybe have an example? Sure. So something that has come up in the linear algebra class. They have something where it's like prove that like let's see. prove that A plus IB times A plus IB reciprocal is equal to 1. So if I wanted to prove this, and I would, I guess, have like for every A, B in the real numbers, prove that this is true, prove that that's the case. Well, so if I wanted to prove this, I could, well, first of all, if I didn't think it was true, I could try to find some A and B, and where I is equal to the square root of minus 1. I could try to find some A and B where this wouldn't be true, or if I did think it was true, I could provide a proof. And so I would start by saying like the left side is equal to, and then write out the left side. And the reciprocal, this is 1 over A plus IB. And this you could write is equal to A plus IB over A plus IB, which is equal to 1, which is equal to the right side. So here I've just provided a proof that the left side does in fact equal the right side. So that would be an example of a proof. But let's say I had something like for every set A and B, which are subsets of our universe, A intersect B is equal to the empty set. And let's say that our universe is equal to the set containing 1, 2, and 3. Well, so I could prove this false by saying, well, let's let A be defined to be equal to the set containing 1, and B be defined to be equal to the set containing 1, 2, and then do A. So from that, it would follow that A intersect B is equal to, is equal to 1 intersect 1, 2 is equal to the set containing 1, which doesn't equal the empty set. So there I've found their claim was that for every AB, which are subsets of the universe, A intersect B is equal to the empty set. Well, I then found two subsets of our universe and showed that their intersection wasn't the empty set. Does that make sense? Cool. Not necessarily. So I'll draw this table again. So there's sometimes there are arguments where it's like for every, and then sometimes there are arguments where it's like for some. So like this argument up here was saying for every B, actually here, yeah. So for every A and B that's a subset of our universe, this is true. And so that's it's a question of where it's for every. And if you think that this is a true statement, so we have truth or false. So if you think a statement where the claim is for every such and such a thing is true, then you have to provide a proof that it's true. But if you think it's false, you just have to find one witness to the falsehood. And if you have a question where it's like there exists some, for example, with this universe, I could say as a different question, let me just hide the chat for a sec, that there exists some A, B, which are subsets of the universe where A intersect B is equal to the empty set. Well, then you could find a witness to this, because this is just saying that, hey, there's at least one, possibly more, the backwards E. So then we could just say let A equal to, A be equal to B be equal to the set containing 1. Oops, and I didn't write a B, I said a B and I wrote an A. So then we would have A intersect, oops, sorry. That would be dumb. A is 1 and B is 2. So then we would have A intersect B is equal to 1, set containing 1 intersect the set containing 2, which would in fact be the empty set. So there we would have shown that this statement is true. So if the question is asking that there exists some such that something is true, then you just have to provide a witness. But if there are none that satisfy that, then you have to provide a proof. Does that make sense? Yep, you're welcome. This still, oh yeah. I can't tell if this is actually recording. I think there is one that's recording. I apparently have 2 of these open. Yes, I do. Cool. Any other questions? We got about 13 minutes. Does anybody have any more questions? I guess you guys don't have any more questions, so I guess we're done. Yep, you're welcome. Mm-hmm. Are you on the Discord? So there is a channel called Recitation Archives. They should be there. You're welcome. Yep, you too. See ya.